Okay, yeah, thanks everyone for coming and thanks for the introduction. Um, Let me just see if I can hide this one. There we go. Okay, now I can see the full screen. Yeah, so I want to talk about our work that we have done over the last few years on world models for embodied AI and especially for continuous control. And we've been working broadly on RL algorithms and world models for a lot of different domains. Some of them are shown here on the slides. Includes single arm manipulation, dual arm manipulation, humanoid locomotion, autonomous racing, and much more. But yeah, let me first start by explaining some of my research philosophy. So a lot of the AI agents that we're seeing today, which I'm sure you're all very, very familiar with, they're all more or less generalist models. For example, if you have an iPhone, you can take a photo of your couch in your living room, and you can ask the model for tips on how to decorate the room, and it will give you a pretty reasonable list of ideas for things that you can do in your room. And similarly, we also have text conditional video generation models that are able to take a fairly detailed description of something that you want to generate, and it's able to generate these short horizon, high fidelity videos of what is in your prompt. And I think the key idea here that is most exciting to me is that it's a single algorithm or model usually that can be applied to a lot of different problems without the user necessarily knowing any of the details of machine learning or the application itself. So it's really, really general purpose and easy to use. And I think especially having models that are easy to use for people that are not experts is really important. So you're all very familiar with this, but some of the key ingredients for building these models include having large, diverse data sets, usually scraped from the internet. With that data, we need some kind of scalable architecture that can consume all of this data. Usually that's transformers or some other scalable architecture. And then the last key component here is having an objective that is general enough that we can actually reapply the same model with the same training data, but then use it at test time for many different applications. For example, next token prediction is what's most commonly used in language models at the moment. Now, this brings us to embodied AI and my vision for the future in embodied AI. I believe that world models are a very key component in the future because world models allow us to reason about the physical world in ways that model-free models and policies will not be able to do. And I'll come back to exactly what I mean by reasoning. But I want to also make a different point that world models, they're predicting the world future. So conditioned on the current state of the environment, we're predicting what will happen if we take certain actions. And I would argue that predicting the future based on the past is probably the most general objective that we can design when it comes to embodied AI. There are some examples of this already in different companies. So 1X Technologies, they work with humanoid robots. They have designed a world model that conditioned on a frame here, ecocentric frame of the robot, and a sequence of actions is able to simulate what would happen if you executed that on the robot. Wave had designed a similar model for autonomous driving that is conditioned here on a small sequence of historical frames, and then it's able to predict what would happen if you steered the car in a certain way. And Google DeepMind have applied this to video games as well, where they are able to generate short horizon video game experiences based on single frames, and you can control these worlds by keyboard instructions. So what I mean by reasoning here is that given a single frame, a world model is able to simulate what would happen if we took certain actions, and that means we can generate counterfactuals. So given the same state, we can generate multiple different futures and then decide which ones is more desirable and which ones we want to avoid. This is something that video generation models like Sora currently can't do. They are able to generate also high fidelity videos, but there's not action conditioned. So we can't actually generate these counterfactuals with those models. So I want to talk about how to actually build a world model for control specifically. And my definition of a world model is it's a model of the transition function of the environment. So it's a function here, capital T, that is conditioned on the current state of the environment and an action, and it's able to, it's a function we can sample from and get a next state of the environment and potentially also a reward if we're modeling a reward function as well. Now, assuming that we are working with reward functions, which is what I'm doing in my work, we can use the world models for planning, meaning that given a single state, we can simulate multiple different futures, and we can select the sequence of actions that maximizes the reward according to our model. So there's a few components that go into building a world model. Generally, you have some kind of observation space, which might be states or images or tactile information or any combination of those. We want to build an encoder that can extract features and produce some latent representation that is a compression of the original observation. And then we want to model the dynamics, usually in this latent space. So it's a function that is conditioned on the current latent state and an action taken in the environment. And it's predicting the future latent states recurrently. And then we'll have one or more prediction hats, usually, that we use for supervision or for downstream applications. For supervision, it's common to use things like reconstruction. If it's a generative world model, you might be using contrastive learning or self-predictive objectives if it's not a generative model. And you might also have reward information that you could use both at test time for planning, but you can also use it for supervision at training time. And there's many other ways to design these supervisory signals, but these are the most common ones. So I mentioned generative models. If you're familiar with Dreamer, it's a model-based RL algorithm. So that's classified as a generative model. The way that it works usually is that it takes observations as input, encodes them into the latent space, and then it derives the supervision by recurrently predicting future observations in the observation space itself. And then it's minimizing the difference in the predicted pixels and the ground truth pixels from your data set. The kind of model that I work with is self-predictive. TDMPC here is my prior work. And they are kind of similar, but they apply the supervision in a different way. So they're non-generative. Instead, they also work with sequences of observations and actions, but they instead apply a loss here in the latent space. So we're minimizing the difference between the future latents and the future latents that we get by rolling out our model in the latent space. And if you took those ground truth observations and encoded them with the same encoder, you get a latent state, and we want to minimize the difference there. So it's applying the loss here in the latent space instead of the original observation space. This has some advantages in terms of compute. So being in academia, I think compute is something that we're concerned about. And it also, theoretically, it works quite differently. It's more like they're both lossy compression algorithms, but generative models, they kind of try to compress all the information in the environment, whereas self-predictive models, they tend to favor things that are predictive of say, rewards or controllability. Yeah, those are like technical details, but these are the two classes of algorithms. I want to start by discussing the TDMPC world model, and specifically TDMPC2 here, which is our second version of the algorithm. And then later I will talk about some applications or things that you can do with world models. The TDMPC2 work here focuses on building scalable, robust world models. And here by scalable, I mean that as we get more and more data and more parameters, ideally our world model should get better. We also want it to be robust, so we want a single algorithm that could be applied to different problems. It might not be necessarily a single model at the moment, but at least we should have an algorithm that can be applied out of the box to different control problems. So this means no hyperparameter tuning, for example. I want to show here first how we trained the model. And then I will discuss how we can use it for planning or reinforcement learning. The model here takes the observation as input, encodes it into the latent representation. And then conditioned on this latent representation, we have a few different prediction heads. First, we predict the optimal action. This is a policy that we use as a prior for sampling. We predict the reward, which were given by the environment. And then we also use a value function that we use to bootstrap our predictions. I'll show this in a bit. But then conditioned on an action from the dataset, we are predicting the future latent state. And then conditioned on that latent state, we're recurrently predicting these three quantities again. And so we can do that for some amount of steps. Now, the way that we get the grounding or the dynamics modeling in this architecture is by using this self-prediction objective. So we want to minimize the difference in the latent states here, the Z's, that we get from rolling out our model versus if you took the ground truth observations at those future time steps and encoded them. So the loss would look something like this for the third time step. Is that clear so far?
I think yes.
Perfect. Yeah, if you have any questions, just let me know. I don't think I can see the chat, but you can unmute.
Yeah.
You're going to find the objective more formally like this. So it's a weighted loss or across time. So we weight closer predictions, closer in time, more than the future ones. And then we have three terms here. We have the self-prediction objective, and then we have a reward prediction, and then a value prediction. And we train all of the components in the model end-to-end with these three terms. So there's nothing else. I'm not going to go into details, but this is the objective that we use. Now, once we learn the world model, we can use it for planning. The way that we do it in TDMC2 is the sample-based planner. So it works quite similar to what we do in training. We have a current state or image that we receive from the environment. We encode that into a latent representation. And then we can sample multiple different action sequences from some prior distribution. And then we can evaluate those actions using our world model by simulating. And this is something that could be done in parallel because it's a neural network. And then using those prediction heads that we trained, we can estimate the return of taking those action sequences using reward predictions at each step of the rollout from the model. And then we can bootstrap these trajectories with the value function that we also are learning. And so this means that we have pretty accurate short horizon estimates from the reward function itself. And then we have a heuristic value function that we're learning as well for the long-term return estimate. So we can use this algorithm for both online RL and offline RL and many more things. In online RL, it looks something like this. You might have this like dog environment where you want to maximize the velocity. And initially, you're randomly initializing the neural network. You don't have any data. And then as you connect more and more environment interactions in an online interaction manner here, you iteratively keep training the world model, and then the world model and the planner gets better. And after about 10 million environment steps, you have a working policy. And this is about, I think, 1 day of training on single GPU, single environment. We repeat this for a lot of different tasks. In this paper, we do like 100-something tasks, but at this point, we've done hundreds of different tasks that we have applied the algorithm to. And we want to solve all these tasks without any hyperparameter tuning. We both solve individual control problems here by running the algorithm on each problem. And we also train a single model that can do all of these tasks at once. The single task results, where we just apply our algorithm without tuning to each of the problems. We have about 100 tasks. We categorize them in 6 different domains. And the y-axis here is either reward or success rate, whichever is defined in that benchmark. And we compare it against a few other standard algorithms like Self-Test Critic, which is model-free, Dreamer, which is model-based, the generative model that I discussed before, with TDMC1, which is the first version of our algorithm. This one, TDMC1 here, did require hyperparameter tuning. Now we have TDMC2 here, which does not require hyperparameter tuning and tends to do slightly better across all of these different problems. So this is pretty exciting. We have an algorithm that can be applied to all of these different problems without any tuning. We're also able to scale the model in dataset size and also model parameters. So here we have another experiment where we have 80 different tasks from different domains. And we have DM control and MetaWorld here. We just train one model on all of the different tasks that are in these domains. And it includes, I think, about 15 different embodiments. So we both have to deal with different tasks, but also different embodiments. And the x-axis here is model parameters in log scale. And then the y-axis here is denormalized score again here, which is reward or success rate. And we see something interesting here. We see that as we scale the number of parameters, we get gradually better and better performance. Now it does at about 50 to 300 million parameters, it does plateau a little bit. I think that's because we're saturating the benchmark a little bit. We're running out of data essentially, and so that's something that we would like to do in the future. But it's nice to see that we get this scaling because that's not a given when you do reinforcement learning. I imagine many of you have worked with RL algorithms before, and they don't necessarily get better just by scaling the number of parameters. But we've been able to achieve this. There's some reasons that it's scaling. I'm gonna skip over to some of them, but if there's interest, I'm happy to elaborate later. We do see that planning is quite important. So these are multitask ablations. The red one here is with planning with the policy prior. The brown one here is planning without a policy prior, so just a standard Gaussian. And then the gray one here is if you remove the planning and just learn a model-free policy using the world model, which is what a lot of previous work does. And it does seem that if you're in a multitask setting, learning a multitask policy is actually really difficult compared to planning. We also have things like normalization in the architecture. This makes scaling better. We redesigned the regression to be discrete instead of continuous. This also helps a little bit. And there's many more tricks that you can check out in the paper. So all of this is publicly available. So if you're interested in learning more, there's a link here, tdmc2.com. We have all of the checkpoints that we trained for the paper, so more than 300. We have data sets for all of the data that we train on, and we also have code for training and evaluating policies for your own domains. It's pretty easy to set up. So yeah, if you're interested, definitely check it out. Any questions to this part before I move on to the next?
Yeah, can we go to the single RL experiments?
Mm-hmm.
Yeah, this slide. Yeah, so no hyperparameter tuning, do you mean that we use the same set of hyperparameter for the same environment of all tasks or all environment of all tasks?
Yeah, so we have 100 and something tasks with one set of hyperparameters. So one set of hyperparameters across all of the different domains and the different tasks in those domains.
Okay, so all the experiments are conducted on one set of parameters.
Yes, yes.
Yeah, great.
For DM control and MetaWorld and Maniscale, the top row here, we used those during development of the algorithm. So you could argue that even if we are able to solve all of those without tuning anything, that we might have overfitted a little bit to those domains. But then we took the algorithm after developing and getting these results, we took the algorithm and then we applied it to the bottom row here without any changes. So these are completely out of the box. And these are results that we ran the first time. So for my suite, for example, here, it's 10 tasks of dexterous manipulation. And these results here are the only time that we ran TDMC2 on that domain. So it's completely out of the box. Yeah. Any other questions? Great. Then I will go to the second part. I'm also happy to send these links later. The second part I wanted to talk about, because I've mostly been talking about learning algorithms, how to build the world model. I haven't really said anything about the training data. So in the previous examples here, we do either online RL, where we're collecting our data by interaction for each task, sometimes in the order of millions of environment steps. The scaling experiments were offline RL, so those are big interaction data sets that we have previously collected. So those are in the also hundreds of millions of interactions. But I want to talk about something that we can actually do in the real world. And in the real world, usually we're a lot more constrained on the amount of data that we have and the type of data that we are able to collect. If you want to do things in the real world, we have a few different options. For example, you can do interaction, which is very cheap if you're in simulation. It's a little bit more expensive in the real world, but it's still doable. The problem with interaction is that you have pretty low diversity in the type of data you're collecting, both in the terms of the policy actions, but also in terms of the environment randomization and the kind of task that you're able to do. But it is the benefit that it's quite cheap, at least in simulation. Another more significant limitation that people don't talk much about is that if you are doing RL, you have to design reward functions. And for a lot of standard environments, we have well-designed reward functions that are sometimes hundreds of lines of code. But that's not really scalable in simulation. And in the real world, we're usually not able to even design reward functions that have because they need all of this extra information that are easy to get in simulation, but not in the real world. So reward design is a big limitation when you do RL. On the other hand, if you do imitation learning with demonstrations, for example, it's very time consuming and can be very expensive. You need to collect data with multiple setups and multiple robots. You do get more diversity. It's easier to get more diversity in the data that you're collecting because you're deliberating. It might also be easier to just pick objects from around you and be able to get more diversity that way, rather than building things in simulation. And the biggest benefit of doing demonstrations is that you have very strong supervision. You're directly supervising the exact actions you want your policy to take. And as you collect more and more data, it will be able to generalize and interpolate in that data distribution more. Now, these are the things that we have access to at the moment. I would like for all of us to think a little bit about our wish list for what we would want in the future for data collection. It's probably some combination of different data sources, but ideally we want something that is kind of scalable in terms of the data collection. We want to be able to collect a lot of data and make sure that we are able to train policies with all of this data. We want it to be high in diversity, so we want as much diverse data as possible, both in policy actions and environments and tasks. And we also want the supervision to be strong. And in the last couple of slides here, there's maybe a little bit more than a couple. But in the last part of the presentation, I want to talk about some of the work that we've done in the world model framework here with these TD-MPC2 world models, but incorporating some of these more scalable and supervisory techniques. And the first idea here is to simply just use both demonstrations and interaction data. We know that demonstrations are very expensive to collect, but what if we just collect a few of them and then rely on interaction for the remainder of the policy learning? As a case study, we have a simple task here. It's a simulated dexterous hand. There's a hammer on the table, and then there's a nail. And here the task is to pick up the hammer and then hammer the nail. And we want to do this from image inputs because we want it to be something that you can run in the real world. And we want to do it with sparse rewards because designing dense rewards functions is both difficult and also it's not really feasible to do that in the real world. So if you're able, like if you are to solve this task with just reinforcement learning, you're starting from scratch, you're doing random exploration, and it's very unlikely that you'll ever get a reward that isn't zero. Because in order to do that, you would have to randomly pick up the hammer and then hit the nail, and only then do you get rewards. So this is very likely to not work. On the other hand, human demonstrations are slow and expensive to collect, but it's very direct supervision, and we're able to demonstrate very quickly how to solve this task. So the simple idea here in this work that we call modem is just to collect a few demonstrations to kickstart our learning process and then let the RL agent fine-tune itself and collect more data after that. The way that it works is that we have about 5-10 human demonstrations that we collect. We pre-train the world model on those demonstrations, and then we allow the world model to interact with the environment and collect its own data. And then anytime we make updates to the model, we use half of the batch is demonstration data, and the other half is interaction data that we collected ourselves. Here's some examples of what it looks like on real robots. So in these examples here, we're doing pixel to action world models. So it's a TDMC world model that is trained on these different robots. So it's one policy per robot. It's trained from RGB images. So there's 3 RGB cameras, and the resolution is 224 by 224, I believe. It's a pretty high resolution. And it's directly outputting actions at each time step. And this is trained with 10 demonstrations and then online RL fine-tuning with sparse rewards. So you only get a reward after picking up the object or rearranging it, depending on the task. It turns out that for some of these harder tasks, like the bin picking and the reorientation task, fine-tuning can actually be very, very beneficial. We have on the right here, we have 2 different plots with the success rates of the policies. The gray one here is if you only do behavior cloning on those 10 demonstrations. So with 10 demonstrations, it's enough to get a policy that is successful sometimes, usually 1 in 5 of the episodes, but it doesn't generalize very well to new states and new actions. If you use that demonstration data as your starting point and then you fine-tune for just 1 hour with online RL, TD, and PC, starting from those demonstrations, you can do significantly better, depending on the task, somewhere between 40 and 70%. And this happens completely autonomously. So the environments here on the left here that we're experimenting with are designed in a way that they automatically reset. So there's no human intervention in that hour. And we only do it for 1 hour because we're working with real robots, but it's likely that if you continue fine-tuning, you will continue to get better and better performance. Any questions to this part?
Yeah, a short question. So how do you come up with the ratio of 50% of mixing up the data samples from both the world models and the human demonstrations? Because it seems that a few human demonstrations might lead to some negative effects of imitation learning.
Yeah, it's a good question. So for this part here, we sample 50-50. Empirically, it doesn't seem to matter that much. I think there's an interesting paradox in deep learning that usually, as long as things are somewhat balanced, things will work just fine. If you use like 50-50, for example, it seems to be working fine. If you make it 40-60, you probably don't see much difference. But if it's an order of a magnitude difference, then you will start seeing different performance. And initially, we tried to do some annealing, for example, where initially you sample more from the demonstrations and then less from the buffer. And then over time, you can change the ratios. So we tried a lot of different schemes like that, and it doesn't seem to matter that much. It seems like 50-50, although it's very simple, it seems to be doing pretty well on average. So I wouldn't say that it's not likely to matter, but it doesn't matter as much as you would think.
we can still we can now still completely get rid of the human demonstration, right? So even though the ratio does not matter that much, we still need a several ratio of human demonstrations.
Yes, yes. Yeah, what I mean is that as you collect more and more interaction data and the policy improves, then you probably don't need the demonstrations as much because your policy itself is getting better. But it is very important to have those demonstrations initially.
Yeah, thank you.
Yeah, the exact ratio doesn't seem to matter that much. Yeah, so that it's a pretty simple idea. It's mostly just changing the data that we have access to. Um, I want to talk about some other directions that we have been working on. Um, the previous work here, we're doing sparse rewards, image-based RL, and then using demonstrations to overcome this exploration challenge. But we're still doing RL with sparse rewards in that case. So in this work here, which is something that we're going to be presenting at ICML this summer, um, we're investigating whether we can learn dense reward functions and improve the sample efficiency of the RL fine-tuning process after we have collected the demonstrations. And specifically, we target here more long horizon tasks. So tasks with multiple stages, for example, is a pretty simple example here, but a task with 3 stages where we need to pick up this little peck here and then move it to the hole in the box and then eventually insert it. As a sparse reward task, this is quite complicated because it involves multiple grasping and moving. And in the last stage here, it needs to like slightly change its grasp as well in order to insert it. So it's a pretty complex task, especially from images. In this work, we design an algorithm that is based on what we saw previously, but then learning a dense reward function that can help improve the sample efficiency in these multi-stage tasks. And the recipe looks something like this. We have a task, we coarsely define the task stages. So for this task here, we did choose to design it as 3 stages. And then we have a sparse reward for each of these stages. So when we complete stage 1, we get a reward of 1. When we complete stage 2, we get a reward of 2. And then when we complete stage 3, we get a reward of 3. And then based on the same demonstrations that we had before, so these 10 demonstrations, we use self-supervised learning to learn a dense reward function. It's something like training again on the data set. And this gives us this discriminator, which we can directly use as a reward function. What the discriminator is doing here is that's predicting whether you're in stage 1, stage 2, or stage 3. And then we're assigning rewards based on the probability predicted by the stage discriminator. And if you have a dense reward function learned from data, you can simply run the previous algorithm. So use those 10 demonstrations, pre-train the world model, and then do online interaction where you sample 50% from the demonstrations, 50% from the interaction data. And then you can label all of your data using the dense rewards that you just learned. And if the dense reward function is useful, so better than random, it should improve the sample efficiency. Now you're collecting data as you're interacting, so you can also use all of that data to train the reward function on more and more data. It's not strictly necessary, but we do see better performance if you do that. Here's an example of what the reward function looks like. So we have a trajectory here on the left, which is successful in this case. And then we have the reward over time here during the episode. And you'll see that it starts pretty close to 0. And then as it's completing the insertion here, you see that it increases the reward. It fumbles around a little bit and actually almost loses the peg, so the reward goes down. But then when it reinserts, it goes up here and eventually reaches 3, which is the maximum. Here's an example of the same task, but where the robot fails to insert it. You'll see here that anytime it grasps, it gets a higher reward. Anytime it gets closer to the peg, it gets a higher reward. but then when it eventually fails, it will get a reward around 0. So it does seem that the reward functions that we're learning tend to correspond to the stages pretty accurately. We run some benchmarking here in simulation. So we have 4 different domains and multiple tasks in each domain. We have some many-skill task here with a single arm robot. We have meta world. We have a humanoid robot. We're doing upper body manipulation. And then we also have this last robot from Robot Suite. And all of these benchmarking results are with between 5 and 25 demonstrations, depending on the task. Some of the tasks are more difficult than others. And then we have about 100K interaction steps. For the first environment here, the leftmost one, the tabletop manipulation, our method here, which is the blue one, gets about 76% success. If you were to do TDMC2 from scratch, it's the red one here, you get 0% success because it's a sparse reward setting and you're not actually overcoming this exploration gap. If you use modem, which is the previous idea 1 here that I showed, which is doing pre-training with the demonstrations and then online fine-tuning with a sparse reward function, you get about 34% success after those 100K interaction steps. So it is learning, but it's taking longer than if you have a dense reward function. And then also here we have, this is a brown one here is a baseline, and then the gray one here is behavior cloning, same as before. You take those 10 demonstrations and you learn a behavior cloning policy. We can do this in other domains, and we see a pretty consistent trend here that in all of these domains here, TDMC2 is doing not that great because it doesn't have demonstrations. Modem here is doing better, but it's still not quite matching the sample efficiency of our method. And behavior cloning is consistently a lot worse. The one limitation of this line of work is that we're learning task-specific policies, and we require task-specific demonstration data in order to solve those tasks. So anytime we need to learn a new task, we need to collect a few demonstrations, and then we need to collect some online interaction data. This means that we're able to do single task pretty efficiently, but it wouldn't really work in a multi-task setting, at least not with the current framework. And this brings me to the last idea that I want to discuss. We're moving on from manipulation now. Now we're going to talk about humanoid locomotion. Unless there's any questions first. Right, I'll continue. Yeah, we're going to talk about human locomotion. Specifically, I want to talk about visual whole body humanoid locomotion, meaning that we're doing locomotion where we're controlling the full body of the humanoid with all the joints, which means that it's very high dimensional action space. We want to do it from visual inputs. We want to do locomotion with obstacles, so we need vision in order to perceive the environment. And we want to do locomotion as fast as possible. So we want motions that are natural, but also run in a certain direction with high velocity. And the one thing about locomotion compared to manipulation is that it's easier to design simple reward functions like maximizing velocity, but it's very difficult to design reward functions that describe natural motions. So for a simple reward function like running forward as fast as possible, there are many different motions that are able to maximize velocity, but humans have a preference for which kind of motions we are generating. And that's not usually something that you can describe in code. So in this work, we decide to use human mocap data, large-scale human mocap data sets, to describe what is a natural human motion, and then use that as a prior for generating humanoid locomotion. Specifically, we're using this CMU mocap dataset, which is about 20 years old at this point. The idea is pretty simple. We first take our world model, our TDMC world model. We pre-train it on a simple tracking task where we take the the human mocap dataset we sample in simulation here. We retarget it to our humanoid embodiment. And then in the simulator, we sample a sequence from the dataset. And then we task the robot here. The orange run here is the one that is controlled by our robot. We task the robot to track the motion in the dataset. So here the orange one gets reward for matching the key point positions in the yellow one and the gray one here, which is the reference. And we do that for all of the data in the dataset. So there's more than 800 different motions that are sampled. Many of them are locomotion. Most of them are locomotion in the dataset. And we train a single world model just by online RL by just sampling different sequences and just tracking those sequences. The world model here is, as I mentioned, it's TDMC2. It takes the joint positions as input, as well as the key points of the reference motion that it needs to track. And then it's simply trying to do tracking as accurately as possible at each time step. Now, after learning this tracking world model, we now have a generalizable tracking world model that is able to track all of these different clips. We can save this world model and then we can reuse it later for downstream tasks. I want to show here first some tracking results of what the tracking world model that we trained looks like. So there's more than 800 clips in the dataset. Here's just tracking results on a small set of them. You'll see here that it's not perfect, but it's doing pretty well overall. We don't have any way to distinguish the different tasks. Everything that we give here to the model is just joint positions and the key points that it needs to track at the next time step.
Already cut in. So what's the exact supervision for the tracking world model is a little bit confusing to me compared to the conventional world model because it's a tracking world model, right? So is it supervising is it predicting the future motion of the reference tracking points?
Yeah, it's a good question. Let me be more precise here. The world model here is a TDMC2 world model. The observation space is all the joints in the orange humanoid, and then the key points in the gray one here that it needs to track. So it's conditioned on a reference motion. And then the action space of this one is every single joint in the humanoid. So there's 56 degrees of freedom. And so that's the action space of our world model. And the reward that it gets at each step is the mean squared error between all of the key points in the orange one and all of the key points in the gray one. So it's just minimizing the difference in its positions. Yeah, you can train this with TDMC2 or another RL algorithm without any changes. You just need to design the observation and the action and the reward function.
Yeah, clear enough. Thank you.
Yeah, that's a good question. Yeah, it's very simple. It's just TDMC2 with no changes. The only thing that we designed here is the reward function and then the observation space. Yeah, this gives us a world model that is multitask and able to solve all of these different tracking problems. We're leveraging, again, the fact that it doesn't need hyperparameter tuning and it does tend to scale with more data. So we don't actually change the algorithm at all. Now, once we have the tracking world model, we additionally train what we call a puppeteering agent. A puppeteering agent is the model that is controlling or steering the low-level tracking world model. The tracking world model here is a reusable model that we trained before we pre-trained it, and now we're not training it anymore. It's able to track these different reference motions in terms of the key points. And then the puppeteering agent here that we train on the downstream task, the action space of this one is key points for the low-level agent to track. So the puppeteering world model here takes joint positions of our humanoid here in the downstream task as input, as well as the image that we're seeing here. So it's a third-person image. And then based on that image and those joint positions, it's producing commands for the tracking world model to execute at the next time step. So the puppeteering world model here has a lower dimensional action space, and the tracking world model has a higher dimensional action space. The difference here is that the tracking world model is trained on human data. So it's trained on tracking, and it's trained to track motions in a natural way because that's the data set that it's been trained on. But the tracking world model itself is blind and it's not task specific. The puppeteer world model here is trained with the additional vision input for the downstream task, and it's just producing these high-level commands for the tracking world model. Something that is a little bit surprising, perhaps, is that if you freeze the low-level model that is trained on human data, and then you train the high-level model on the downstream task, still with a simple forward velocity objective in the reward function, it still retains the human biases of the data set before because the tracking world model is not changed. You could imagine that you could train a TDMC2 policy without hierarchy, so just a single model on the downstream task, and we'll see some examples of what that looks like. It does work, but it doesn't look as natural as if you have a pre-trained tracking world model. Hopefully this is somewhat clear. I want to show some examples. I think that makes it more clear. Here's the gap task that I showed before. So we want to run forward as fast as possible. There's gaps in the environment here that we need to use our vision to perceive and avoid. And if you do train with human data, which is on the left here, you see that it has a pretty natural gait, and it's generally able to run in a way that is stable. It's still not perfect. It does fall eventually, but it's running pretty consistently. If you train TDMC2 with no human data, just a end-to-end online RL framework, you get something that still runs pretty fast, but you see that it looks much less natural because it doesn't have any notion of what is a human motion. It's just maximizing velocity. If you look at the reward here, which is the forward velocity in the episode, you see that Puppeteer and TDMC2 are actually very, very similar. So they both run with the same velocity, but the puppeteering agent looks much more natural because of the human data. Similarly, here is a different task. This is a hurdles task. So there's these small red pinkish hurdles in the environment, and we need to run and then use vision to step over these hurdles. And you'll see here at Puppeteer again has a pretty natural gait. The TDMC2 policy here achieves more or less the same reward, but still it has a gait that is very unnatural. It's doing these strange flips. So I want to just summarize what I've presented here. World models in general, I think, are very promising for these more generalist embodied AI problems. What we have right now is a single algorithm that can be applied to many different problems individually without tuning, and it's able to do quite well. We have some initial results of these multitask world models that are trained on bigger data sets, and we do see some promising results in terms of scaling. We're mostly bottlenecked by data right now. So more work like the Puppeteer work where we try to use large-scale existing data for training. I think that is very promising. We're going to see more of that. But we do have a framework that is quite flexible. Yeah, as I mentioned here, combining multiple different sources of data and supervision can be very beneficial. So if you want to do research in this area, I think it's very interesting to think about how we can creatively use different types of data, whether it's demonstrations or human videos or online interaction, whether it's learned reward functions, whether it's self-supervision, whether it's sparse rewards, all of these different techniques, how we can combine those to build something that is very data efficient. And I think it's also interesting to still think about how to scale to truly large data sets. We have seen things in the order of 100 different tasks. If you want to do anything in the real world, we have to face reality that we have many different robot embodiments. So you can imagine, for example, in the more like Puppeteer line of work, you might have tracking world models that are trained on a lot of data for a specific embodiment. So it's able to move around and control the robot here in the environment in a way that is stable and is able to track the commands of a human or some other model. You could imagine then that you could train like a bigger puppeteer world model that is conditioned on images and maybe a language instruction, doing more or less the same as what a human would do with a joystick. And then using this puppeteering world model, it's able to command the individual tracking world models to execute different motions, while all the physics-specific things are offloaded to the tracking world models. Whether this puppeteer world model is TDMC2 or it's a VLM or something else, I think that's very up to debate. But you could imagine something like this in the future. I want to end by just saying thank you to my advisors, Professor Xiaolong Wang and Professor Hao Su, and all of the collaborators that have worked on these projects. These are all students at UCSD, and there's some collaborators at MedAI as well. Yeah, thanks.